little bit different than that. We're going to be a case study talking about what we're doing at Laureate and how we're putting it into practice. So for the people from Sun, please know where my challenges are. For everyone else, I hope we can have some conversations about maybe what I should do or about what our future holds. So the Laureate's Institute for Brain Research, we're biomedical research. We are sort of funded by a private foundation in Tulsa. Tulsa is kind of unique in that we have a lot of philanthropy. And what they said was, we're wasting our time, we're wasting our efforts, we're wasting our money with doing research in for-profit hospitals associated with medical schools. So what they decided to do was they brought a sort of our patriarch, Dr. McKee, in from Duke, and they said, okay, you have a ton of money, what do you do with it? He said, well, I spent some time at Framingham. Framingham was basically the most important cardiac study that's ever existed. It was a long-term, 20-year study, and it was built really with no experimental design besides finding out about the heart. So with this large populations and kind of very small, not small goals, small goals, but over a very massive project. It built up with lots of small goals. It brought us sort of what we know about the heart, what we know about risk factors. And so with that in mind, they said, let's take that same study design, long-term study, huge patient population, combine it and find and apply that towards the research that we have in Oklahoma. What resources do we have? We have a psychiatric hospital that has a well-known eating disorders program. It has 80,000 depression patients that it sees per year. And what we get to do is combine the neuroimaging data, the clinical data that they already have, apply it to their own patient population, also correlate it to DNA, protein, RNA, and epigenetic factors to find the root causes of neurological and mood disorders. So we combine all that data and we get what? Well, we get a complete mess of data that we don't know how to analyze. When we look at this data, what we see is the vast majority of our data is neuroimaging, and specifically functional MRI. A normal MRI is a sort of static picture of your body. A functional MRI is that picture, but it's a time sequence. So if a normal MRI is, I think it's most of them are 300 or so megabytes, a functional MRI is 3 gigs, and then the raw form of that is 20 gigs. What we want to be able to do is keep not only the structural part, the temporal part, but also the raw form of that data, because the physicists that we deal with sort of analyze that data in different manners. We'll be going back to our patient population and saying, okay, we now have better physics, we have a better understanding of how all of our components interrelate. What do we do with it? So we need to be able to store a lot of data, and minimum we're looking at about 50 terabytes of acquisition data per year, not including the temporary files and how we process that data. Most functional MRI studies are 20 patients. We're aiming for 1,500 a year. I think the largest MRI study today is 300 patients or so. We're looking quite a bit more. So if we look at our neuroscience data, our functional MRI data, our PET data, our archive storage is how large the scan is times the number of patients. We didn't have to redact a portion of that information, and we call that HIPAA. So what that is information that is medically necessary, we strip out. So this is things like social security number, patient name, patient ID, and this then has a sort of database field that is just basically a random number for all intents and purposes. And then what we found is with this patient data, you give a MRI of the brain, you can run analysis programs on it, and it can generate a face based on looking at the MRI of the brain and the structure of the bone. So we also have this redacted set of that data where we sort of map it onto a idealized model of the human brain, and then so that becomes a redacted data set. So from our 15 terabytes per year, we then are taking that times at least 4 or 5 when we look at the HIPAA set, redacted set, and the different working sets that we have for examination. And those are sort of different steps in the neuroimaging analysis process. So since this is multidisciplinary research, it's not just neuroscientists who are working with this data and physicists, it's computer scientists. So we're going to be working on ways to analyze this data in new methods, new techniques, and also apply some HPC sort of type of analysis to it. So we look at the data once again. We start doing data correlation between the clinical data, the DNA, the protein, and the images. And we're now going to a state explosion of data. For every factor that we put into our analysis, we then have to increase our data analysis capability and our storage capability to work the data by that much. So this turns 15 gigabytes of raw data into terabytes. It's computationally intensive, it's RAM intensive, and it's storage intensive. So our workload. Most of our data is, we write it once, and we're going to let it sit there maybe 6 months, maybe a year before we read it again. However, when we read it, we're going to read basically all of our data at once, and it's going to go to our analysis servers. So most of our data, once it's written, it's never touched again. However, we don't need that much speed when we're acquiring the data, because from the scanner, I think the scanner connects at 100 meg pipe, and it's not even pushing that. So from the scanners to the storage, it doesn't need to be very fast, but from the storage to our analysis servers, we want that as fast as possible. And when we analyze the data, we're not writing back the same amount of data, we're writing back statistical averages, and we're writing back sort of combined data sets that correlate different parts of the brain, or parts of the brain to protein. So usage-wise, we have much more data that never changes. Once we make those redacted sets, hit the sets, we don't need to change that. And but from there, our investigators make many copies, and sort of our data can't be offline. We can't use a typical HSM because the data is used in spurts. We have to have everything online and accessible for when our investigators need to use it. So if we look at our investigators, we can break them down into a bunch of different categories. The first category, probably the most prevalent, is the neuroscientists. These are PhDs in psychology, in clinical psychology, and psychiatrists. And what they care about is they need to just be able to store their data and be able to access it, and needs to be able to be used by sort of lay computer people. The physicists, they need the data, and they need the storage always be online. Since we're acquiring data from our research institute, sort of 8 hours a day right now, probably expand to 16 hours a day. The storage always needs to be available for them. We can't have long backup windows, and we just need to be able to present our storage array as NFS or SIS to the scanners. The computer scientists, we care about speed. When we're analyzing this data, we want to be able to pull as much from our original data sets as possible, take them through the analysis tools, and then get results. Currently, right now, when our scientists are doing their analysis routines, they're copying the data onto their desktop. They are then running commands on it, and they're letting it sit there for 2 weeks, sort of while doing background tasks. This is an incredibly painful process, because if during those 2 weeks you get a power glitch, or any other problem happens, their data is lost. They have to restart over. We're moving to a more centralized model with powerful sort of central beefy analysis servers, and we are preventing sort of the need for that desktop data processing. Some of our other people that we care about are psych nurses. They need to be able to access databases. Right now we have a MySQL database. We're going to be transitioning that to MySQL, and we need to be able to provide these so that everyone can use shared file system and sort of the office type files. Some of the constraints that we have is we need to provide value to the foundation. We're foundation funded. We don't really have a budget, which is a good and bad thing, but we need to be able to have anything that we buy vetted. We want to be able to say we're providing good value to them. So as we went through our selection process, we needed to ensure that. We need to ensure that we fit into the current processes that currently exist in the hospital and at the researchers. Most of our researchers were stealing from the National Institute of Health, and we're moving about 50 of them over this summer, maybe a little bit less. And it needs to be easy to use and easy to administer. The plan right now is 1 full-time system administrator, and then we'll have 4 or 5 computer scientists, another 4 or 5 computer science interns. So if we look at some additional constraints, technically what are we looking for in a solution for neuroimaging? We're looking for Windows, Mac, Linux, and Solaris compatible. Our desktops are going to be a mix of Windows, Macs, and Linux. However, we're going to have servers or analysis servers running OS X, Linux, and Solaris. So what we needed to do was avoid the ACL hell that can exist with a lot of other solutions, especially between NTFS and NFS version 3. And we need to be able to have our data accessed locally via those protocols and remotely via the WAN from FTP and web. So we look at our infrastructure, and sort of the other pieces that we put together is we decided to go 10 gig. Originally we were looking at InfiniBand, however we decided we didn't have the needs, and since sort of 10 gig is becoming cheaper, more plentiful, we decided to go 10 gig, and also it seems like there's more support for storage devices like the Sun 7000. We need to be scalable. Right now, our initial install is 100 terabytes raw at our main site and 100 terabytes at our backup site. We're planning on scaling that out to probably the max capacity of the 7000 series, somewhere along 688, with potential that could grow to, I don't know, 1.5 petabytes in 3 to 5 years. And we need to be able to dissect the data access to the workloads. What we looked at in storage, and we looked at a lot of different vendors, was there was no way like dtrace and sort of being, not a Solaris fanboy, but something close. The ability to really look at our data load was incredibly important to us. So we decided that we needed some way to look at what these analysis programs are using storage-wise. They've never been categorized before. The problem with neuroimaging tools is they are not created by computer scientists. They're created by neuroimagers who are great at coming up with clever, unique solutions hacked onto MATLAB, but they're not great at converting that into something that we can use, something that's portable, written in C, or sort of some of the other languages. So we have a lot of hacks into this entire analysis stack. Another thing that we care about was replication. From our primary site, we're building, I say, a smallish 15-rack data center or so at Laureate. But we also have a bunch of collaborators. University of Tulsa, Vanderbilt, NIH, among others. So we decided to put in the same city our backup data center at the University of Tulsa campus. Having the backup data center there allows us to share data with our TU partners, but also basically piggyback on their internet tooling. So we have a fiber connection from Laureate to the university, and we wanted some way to replicate our data there and have it be available online. We dismissed tape initially, or actually pretty soon, because we wanted to have that live replication. We wanted to have data at both sites. And however, I also, and I might be the minority here, am not convinced about the reliability of tape, especially if you don't know what you're doing with it, which we don't. Another thing we have to care about is we must meet HIPAA. And so there's an entire book of HIPAA sort of standards. It's the security rule. It came into effect 3 years ago, maybe 4 years ago now. And one of the requirements there is encrypt things when appropriate. And going across a WAN link, even though it's a private WAN link, we decided we have that internal requirement that anything sent must be encrypted. And our last requirement was it must be as simple as possible. We had the opportunity, we're starting from scratch, we need the simplest data center, the simplest sort of data pathways we can imagine. And that's what we decided was sort of one of our core tenets is keep it simple, Steve. So if we look at our potential architectures, we have sort of the usual list of storage systems: direct attached storage, SAN plus a NAS head, storage servers, cluster file systems, and direct attached storage NAS. So let me talk a little bit about each one. So with direct attached storage, we liked it. It's cheap. It's something that people know how to use. However, the problem is limited scalability. You run into namespace issues. It's hard to manage the intranode bandwidth if you're doing sort of hierarchies of servers with DAS. It can be a nightmare, and it provides single points of failures. So we decided to avoid direct attached storage. The other option that we were really looking at, and probably will always keep on revisiting, is a SAN plus NAS heads. The great thing about this is you have two very mature technologies, and when you combine them, it's also sort of a mature stack. The problem is, if I can avoid fiber channel when I'm already putting in a 10 gigabit sort of backplane, I'd rather do that than invest in directors. So additional interconnects, we don't have fiber experience, costs. To remove the points of failure, you're spending lots more money, and the NAS heads, performance-wise, are just crap. looking at that one company that represented themselves today, their scalability, they bought Spinnaker Networks 4 or 5 years ago, and we're still struggling to integrate that into their product line. And that's NetApp, and we just didn't get the performance from them, and also their cost for additional licensing just killed us. So we avoided sort of those NAS heads, and then the other NAS heads, there's a lot of very good NAS heads out there. Blue Arc, OnStore. However, just looking at what they provided versus what they didn't provide, we decided not to go with them and to look at other options. But you know, a lot of different pluses and minuses, and for some situations, SAM plus NAS heads makes a lot of sense. Our other thought was storage servers. We're like, okay, we're computer geeks. Let's build our own solution. So we mocked up what we do. We'd say, okay, we can have these storage servers, they mount to each other, or we maybe have InfiniBand back in between them and use InfiniBand RDMA, and then share out via all these different ways. The problem was the complexity. So we have, what we basically have is a bunch of university people, or undergraduate and graduate students, and me going, okay, how the heck do we make this part work? And sort of addressing 15 to 20 different major problems of making these work in sort of a sane manner. Some of the other issues with storage servers was namespace, and that we would still kind of build up all these silos if we architected it incorrectly until sort of like a federated NFS is here. But what we liked was they were configurable, they were expandable. Once again, they were cheap. How we would implement these was probably be the Thunder Thor method. The 4500, 4540, is that correct? The issue with that is the SADA needs are not interposed, and I think that's the correct term, where you have two different data pathways, unlike the J4400. So that's why we decided not to do storage servers, and we just wanted something simple. So we look at cluster file systems. We have things in this area like Isilon, who make a great products, very scalable. However, the vendor lock in there we didn't like, especially if we're looking at the appliance-based ones. We didn't like the vendor lock-in. The costs were kind of high, not incredibly high, but kind of high. And they were very much biased towards read workload, which should work in our situation. However, not knowing what our future holds, since this project basically changes with every new hire, we weren't sure what we were going to do, and sort of that was the right long-term move. And also, people don't read by Isilon for some reason. If you look at their earnings, if you look at their current customers, they ditch them, and that's sort of related to the service of their organization. Is what we sort of figured out. And then what also sort of plus file system-wise, what we looked at was HPC. Things like Lustre or GPFS. They're really quite overkill for what we're doing. They have a lot of complexity, especially sort of when we're in startup phases. I think as we move to more of an HPC analysis environment, we will relook at these. But the other thing is we also didn't know our workload well enough to say, okay, this will be appropriate for this HPC file system, because they all have things that they're good at, even though they're sort of all descend from the same family. So what was our sort of Goldilocks solution? And that was a direct attach NAS. In our case, the Sun 7000 series, lots of sort of, if you look at the space, there's lots of good options. We like the 7000 because of dtrace analytics. Cost was also very good. Scalability, from going from 66 terabytes usable with is what we're looking at right now to 688, I think is what they're saying. That's scalable enough for us right now, and Sun also has some upgrade paths down the line as well. And then we liked it because, hey, we can speak IP, we can speak iSCSI, and it sort of leverages what we already know. Time check?
About 5.
5 minutes? Okay. So this is basically what we decided to do. If we see that far rack, we have our 74 tins. We have 71 tins to play around with the scripting of those. We plan on sort of modifying 74 tins quite a bit and allowing our researchers through some sort of web interface, web portal to manipulate the 74 tin, but we want to test it out first, and that's why we got hardware 71 tins instead of just the VMware image. They're connected to a 10 gig Foundry, this is now a Brocade switch. Then our servers are Sun X4150s and a few Supermicros for some specialized things. So what we see here, and we're just starting with these, is our analysis servers. These are max RAM, max CPU boxes with NVIDIA Tesla video card offloading and an X4600. And that is just startup. My guess is we're going to probably be at 40, if not 45 sort of analysis servers in the next year and a half, with probably another year we'll also be at a rack of sort of a test HPC environment as well. Questions on this? So if you look how it's architected, from our server room, we had a lease line to the university where we have a redundant 7410, 7110, and analysis server there as well. Our current plans, and these change daily depending on who gets hired, is more power. So like I said, we're going to speed up the current tools and techniques, and a lot of these we just have to throw more processors at it. So we're going to look at more X4600s, Tesla offloads. I think that should say convert to native C instead of the MATLAB code that is currently running. And then we'll also try to speed up with new tools and techniques, looking at different architectures. Maybe the ROC for real-time MRI, where you're correlating 16 to 32 different MRI streams at once. We're looking at ROC for that analysis and power architecture, potentially offloading to the cell. We really don't know now. We're sort of in investigation mode for a lot of different things. And then to scale out, we're going to start with a small HPC test cluster, probably in 6 months, go to one rack in probably a year, like I said. And then storage for that, who knows, but right now we're thinking PNFS and ASIS and our Luster. So, our storage expansion, what we're looking at is upgrading the 7410s to full capacity. Potentially, depending on CPU level, we might get additional 7410s in the cluster configuration. But we're hoping that dedupe comes sooner rather than later, since that's going to help our workload quite a bit. That might actually halve the amount of data that we're storing. And then upgrade path to increase speed is Sun has a box called Genesis, which is not J4400 based. It's a lot of disk, a lot of throughput, and a lot of processor cores for data management and manipulation. Sort of one of our fun research plans is we have a thing called LISA that we're sort of dreaming up through Laureate integrated storage and analysis. And what we're trying to do is take the HPC approach of integrated bricks, of building bricks of data, combined storage, combined analysis, and we'll generate this sort of, I guess, internal product with some sort of distributed parallel fault tolerant file system on the back end, some HPC management. But what we're really trying to get is something that we can distribute to other labs that is so simple to use, so simple to operate, and sort of combines all their software, most of the software in this realm is open source, plus sort of scalable storage. But we're sort of in playing around phases with this. And it might be a virtual file system sort of layered on top of the 7410s, or it can potentially be something based on Senia's XAM. So we don't know what this holds, but it should be a lot of fun. So we have a conference coming up in Tulsa, Oklahoma. I know there are a few people from Tulsa, sort of the Midwest here. You guys are more than welcome to come. We'll be having a storage HPC panel with at least one of the guys from the Texas Supercomputing Center. And then feel free to contact me if you have comments, suggestions, or questions.
Are there any questions in the room?
Madam Leventhal, I was wondering, what data do you have to suggest that dedupe is going to be a big win in your environment?
Because so if we take one of our data sets and we make the redacted data set from it, let's say we're just removing the medical ID at that point, and maybe some embedded metadata from the actual file format. From that, we're seeing that would be 95% of the same data. We're just taking out tags and basically taking out metadata and maybe one or two fields of actual data.
And when you talk about taking it out of the file? Are you talking about sort of shortening the file, or is it a bunch of disjoint files all in one directory? Or
It's a bunch of disjoint files all in one directory.
Great, thank you.
I have a question from Bob Murphy on the webcast. Is the 7410 installed?
No, nothing installed right now. We have our server room being built. The POs are being generated this week, and we're basically installing everything in the next 3 months, hopefully. The goal is sort of next month, sort of, if we get the POs out now, we'll have APC in the power taken care of. A few weeks later, Foundry will come out with the networking. And then I think it's that next week's on schedule to come out with the cluster and 7410 install at Laureate and at the university.
Thank you.
All right.
We have one more question.
So if you're HIPAA compliant, how long do you need to keep the data?
7 years.
7 or I thought it was like much longer.
What I'm being told is 7 years. And I'm gonna, if there's a question on that, I'm gonna double check. NIST produces some really nice guidelines, the 866 series. That's part of their special publications on sort of HIPAA compliance. So we're trying to follow that, and that's what the federal government is mandated to do. We're following that because grant-wise, if we say we're compliant to the federal government style of HIPAA compliance, I think when we're looking at applying for these NIH grants sort of starting next year, that's going to help us out. But our HIPAA compliance, our plan is that we're going to be taking snapshots of that daily, and we're sort of, I don't want to say poor man's worm, but that's what we're doing. Snapshots of that replicated to the secondary site.
All right. Thank you very much, Alex.
Thank you.